Welcome to the launching and the initial training workshop for the Watershed Management Modeling System 2.0 of Los Angeles County. My name is Steve Carter. I'm with Paradigm Environmental. I'm the project manager. Introducing this model on behalf of the Los Angeles County Flood Control District and the county's project manager, TJ Moon. We're going to give an overview. It's about a 3-hour training session, going to be broken up into 2 different segments. The model is formally released on a website that can be found at Los Angeles County. If you've accessed this training module, then you have likely accessed that modeling system because these training sessions will be posted to that website once complete. Just a brief overview of our agenda. I'm going to give a background of the objectives and the history of development of WMMS. It's actually 2 component models, so we're going to break the training session up into different aspects, the first of which would be the baseline hydrology and water quality model. That'll be presented by my colleague, John Riverson. There'll be a separate phase 2 training session that will cover the BMP model and optimization framework. John and I will be joined by Paradigm's Dustin Bambick and Ryan Edgley to provide an overview of that system, as well as different newer systems, including Los Angeles County Stormwater Capture Dashboard. That's a part of RAMPS. If you're familiar with that, Dustin will go over that. And then ultimately we'll end with a demonstration of the optimization framework. So just a history of WMMS 1.0. The original model was developed between 2007. It was released in 2012. The county had a vision of development of a comprehensive tool that can support watershed management, TMDL implementation planning. Most of you know it's the use of WMMS and supporting reasonable assurance analyses. We'll get into that a little bit. The original model was developed in partnership with EPA. And has received some nationwide recognition, has been referenced repeatedly within published literature. Just an overview of the component models. So WMMS is a modeling system. It's a system of 3 different models. The first is the loading simulation program C++. That is the baseline watershed model, provides the ability to simulate historic flow and concentration throughout county watersheds. That is linked to a separate BMP model based upon EPA Sustain that provides simulation of BMP processes and associated pollutant reduction. And then a newer component of the system is this optimization framework that allows the identification of cost-effective implementation scenarios to inform watershed planning efforts. Next slide. Just a brief overview of LSPC. John will be covering this in more detail. I mentioned it provides hourly simulation of flow and water quality. It's been originally in WMMS, it was calibrated based upon available monitoring and flow from mass emission stations throughout the watersheds. So this is the same basic modeling framework that was used for the original WMMS. Next slide. Originally, we had the model configured for all the county's watersheds, including 2,655 sub-watersheds. Next slide. The primary input to the model was different land characteristics. We refer to these as hydrologic response units, or HRUs. The interesting thing about the HRUs is that it was based upon the best available information that we had at the time, which was 10 years ago. When John talks about the updates to this model, there's been some significant improvements to these HRUs and our ability to parameterize the model for each of the different land characteristics, which greatly improves the model accuracy. Next slide. Just an overview. This is the original Thiessen polygons associated with the different rain gauges that were used for configuring the model input. Rainfall serves as the primary model input. So it's important to get that information right if we're going to accurately simulate the flows that are resulting from that rainfall. So again, the best for what we had 10 years ago. And there's been some new technological advances and data sets that provided some great improvements to these model inputs. Next slide. That model is linked to SUSTAIN, which was originally developed by EPA's Office of Research and Development. Next slide. SUSTAIN provides what we refer to as a process-based simulation. So it's not assigning a percent reduction, for instance, for different types of BMPs. It actually simulates the processes within those BMPs, whether that process is infiltration, settling, filtration through the soil media prior to outflow through an under drain, evapotranspiration. You can turn these processes on and off and represent a different menu of BMP types. And so we've upgraded all that for WMMS 2.0. Ryan will get into that later in the training session. Next slide. One of the new capabilities of SUSTAIN was what we refer to as this cost optimization. So here you're seeing some SUSTAIN output that presents, each one of these orange dots is an individual management scenario representing a combination of BMPs in the watershed. SUSTAIN provides the ability to simulate different combinations of those types of BMPs to chart out a course towards the most cost optimal implementation scenario using this cost optimization curve. And John will get into the details of this later, but there's been significant improvements over the cost optimization routines. There's been a continued evolution of these processes since SUSTAIN was originally released. They were brought within the original version of WMMS, but we've got new processes and tools to enable the optimization process within the modeling system. Next slide. SUSTAIN has been used extensively throughout the United States. It's been well published in peer-reviewed research, and so we're just continuing the evolution of that modeling system that's in the public domain. Since WMMS was developed, it was used for a number of different purposes, and one of the initial studies that the modeling system was used for was the identification of the water quality design storm, which landed on this 85th percentile storm to cost effectively manage stormwater and provide water quality improvement throughout the county's watersheds. That ended up being the 85th percentile storm that then became the recommendation that was then adopted within the MS4 permit. That's just one example, but there's other examples. Next slide, John. As many of you are aware, the modeling system's been used to support reasonable assurance analyses for the enhanced watershed management plans and watershed management programs throughout the region. Those are due for updates over the next couple of years. So this is a timely release of WMMS to support those analyses. But it's been also been used by the regional board, EPA, and different pollutant source assessments, climate change studies by researchers, and the basin study for LA County, for U.S. Bureau of Reclamation, Los Angeles Department of Water Power utilized it for the Stormwater Capture Master Plan. The list goes on. Next slide. So just some of the objectives of some of the WMMS 2.0 model upgrades, starting with the LSPC model. We actually modified the code itself to provide some improved efficiency. With some of the new inputs that we have the ability to provide refinements to the model parameterization, which led to updates to the calibration, and just taking advantage of the best available information and data that's been released since the original WMMS, utilizing that in the model configuration. But then most importantly, making sure that all these assumptions are transparent, that the model is user-friendly. A number of reasons why we want to make sure that the release of WMMS can be accessible by a number of different users. Next slide. SUSTAIN, I think first and foremost, we definitely want to improve the transparency of the systems and have everyone understand the foundation of some of the assumptions that went into the BMPs for different, for a menu of different types of BMPs, including documentation of the parameters, the cost functions, and overall user friendliness of the system. And then for the optimization framework, we developed a framework that is, again, transparent. We improved the user accessibility, and then with sufficient documentation to guide users on the use of that framework, including a number of tools and utilities that can step a user through that process to improve and expand the user community. And then the end goal of WMMS is just to continue its use in all the various planning efforts, whether it's the reasonable assurance analyses supporting the watershed management programs, pollutant source assessments, even as many of you are familiar with ramps, there's aspects of WMMS that are included within the watershed reporting and adaptive management planning system ramps. And then also tools to enable the implementation of the Safe Drinking Water program and the individual project implementation and conceptual designs and so on. Okay, now I'm going to hand it over to John Riverson to give an overview of LSPC.
All right, thank you, Steve. So LSPC, as Steve mentioned, is a loading simulation program in C++. It's the core watershed model. That's the basis for simulating the runoff and other boundary conditions that are used further downstream in the process and sustain and so on. It's also a key representation of what the current state hydrology is in the region. One of the things that we did originally as part of this effort was to migrate LSPC from the original 32-bit environment into a 64-bit environment. That really improved the efficiency of the model. It allowed it to run a little bit faster. We also created some things in the model to enable for parallelization of simulations. For example, reaches that are not hydrologically connected. You can run them in parallel and in batch mode. So all these things help to really make the model experience a little bit more efficient and also streamline the effort. Another key component of this effort was development of a map. We call it the LSPC map. It's a web-based interface that now allows you to interact with the model. So this really does enable and provide a lot more access to the user community to interact with the model and see relatively where you are in the watershed, the modeled sub-watersheds relative to like a satellite image, for example. You can see where you're actually modeling. So some of these neat things we'll go over as part of this demonstration. LSPC, the original architecture of this model is based on a Microsoft Access database. So all the data that are used in this type of application, whether it be the weather data, the HRUs that Steve mentioned, and how they're all layered together, are very conveniently organized in a Microsoft Access or any kind of relational database environment. So LSPC's input file is this core database. And from there, you can query and send information to the map interface, or query and send information to the model interface, run the model, and then view the results. So it really does provide a nice organizational framework. Here's a view of the map interface for the system. We'll go into this in a little bit more detail, but it is based in a web emulator, so it allows you to toggle between OpenStreetMaps and also aerial photographs, satellite view of where you are in the watershed. Here's an example. You can select a particular watershed that you're interested in running and then launch the model. And when you run the model, it opens up the interface. In the background, it's querying the database for all the terms or information for that selected drainage area. And then it allows you to run the model and then ultimately interact with the results and do whatever you need to do downstream of this process. So again, as Steve mentioned, 2,655 sub-watersheds. That configuration hasn't changed. The model is providing for us an hourly history of the simulation of hydrology and water quality throughout the basin. The gauges that are now included in this new update, we did a lot of update, both the temporal extent of the gauges, as well as including some of the higher resolution, higher density gauge network that the county has. There are about 100 gauges or so that were taken into account and evaluated for data quantity and quality as the first step of this. We also then took and coupled this information with some gridded data products that are also available, NLDAS and PRISM. These are the two data sets that we coupled with. These are modeled data. They're gridded. They're modeled based on observed data within the area. But what this provides is an opportunity to kind of fill some of the spatial gaps that are there within the observed data record. So for example, we have 149 of those blue dots, as you see on the graph, on the map, and then the red dots, there are 551 of them. When you interact and overlay those with the observed data, we get this nice mesh of meteorological conditions over the watershed. And as you can see, it's a much higher resolution than what we had in the original WMMS. And so we're taking into account the best of all these data to fill both the spatial and the temporal history of meteorology in the watershed. Here's a view of what precip looks like, just summarizing precip for all of that combined data set. So you can see it really does capture the spatial variability of the rainfall patterns in the region, the wetter mountains, the drier coastal areas, and so on. So it really does. And as you can imagine, taking the burden off of the model by characterizing the resolution of the spatial boundary conditions for meteorology does take a lot of the burden off of the calibration as well. So you'll see how that translated into the calibration effort later on. Hydrologic response units. These are the land uses, the core elements of the model. A hydrologic response unit is a combination of land use and land cover and soils, slope, and we also had in this case high recharge areas. So when you couple all of these data sets together, we get a nice mesh of information. So we take land use, for example, we have physically what's going on in each of these parcels. We can look at it and look at impervious footprints as well as pervious footprints and distinguish within those land uses where our rooftops are, pavement, roadways, road surfaces, and so on. So it does add quite a lot of texture to what we're doing behind the scenes here in the model. So this also comes into play because ultimately when you go in and we're trying to talk about how we're going to manage stormwater, having this resolution of spatial representation really does improve our ability to represent the drainage areas to each of these different treatment options in our network on the sustain side as well. But this just gives you a view of what's going on in the background. Ultimately, when we take all these land use, land cover, hydrologic soil groups, elevation, and recharge potential areas, and combine them together, we get all these unique combination of HRUs. Here is a view of the HRUs. And when we look underneath, at the end of the day, all this combination yields for us 96 viable combinations that we kept in the model of land cover, soil, slope, and recharge. The original WMMS, we had 20 HRUs. So just for point of reference, we've almost gotten 5 times as many HRUs. What that does from a modeler's point of view is when we're trying to develop a regional model like this, we have one set of parameters for the entire region. Having this texture in our HRUs allows us to have the stratification across the different physical elements that can characterize the hydrology in a much more robust way in the region. So the HRUs, as we mentioned, are the core building blocks of the runoff model. Also incorporated in this effort, in this update, were incorporation of the dams as was done in the original one, but some of these have additional temporal history in terms of the discharge from those dams and so on. So those were extended. We have the debris basins. Those were implicitly represented in terms of their effect on hydrology and water quality at the boundaries. Essentially, they're at the headwaters of most of these concrete line channels. We have these debris basins in place. The spreading grounds and other hydro modifications are a key feature of this watershed. Also, in this region, most of the streams that we have are not natural streams. They're concrete line channels. And so we took advantage of the county's high resolution LiDAR data to actually characterize what's going on in terms of the stream geometry in many of these segments. And so that provided us a really nice way to improve the way that we're representing the, what we call them, the F tables in the model for representing the discharge, volume discharge relationships of the routing elements in the network. The core underlying model behind all of this is based on the Stanford watershed model. HSPF was the basis of the LSPC model. So the key hydrologic components, we track when water comes down from the sky: interception, infiltration, runoff, as well as subsurface water movements. So during the course of model calibration, we set these and we tune these to match what we're seeing in the observed data record. So this fine-tuning exercise takes a number of steps. We do this at the land use level, and then also we take into account what's happening in terms of water movements during stream transport. And in this basin, we try to set consistent parameters region-wide to represent what's happening at the land use level. And then most of the calibration effort that we underwent was tracking down and making sure that we identified all the hydro modifications that were in the stream network. That's what ultimately ended up being most of the calibration effort in this watershed. Our calibration went in a number of phases. So our methodology was to first establish a set of reasonable parameters. So for this, we go to small drainage areas where we can focus in on relatively homogeneous HRU-based areas and set parameters. And then we can go to a slightly larger watershed and look at when we start to combine the mix of these homogeneous land uses together, what happens in terms of their collective impact on hydrology. And then ultimately, validation occurred at the most downstream point, where we're at the main stem. We're taking all the complexity, all of the routing, all of the hydro modifications that are in place, and putting it all together and seeing if our model is able to robustly predict what's happening at those downstream segments. So, validation, calibration. These points that are shown here are the stream gauges that were used for calibration and validation. So at each of these points, we have a time history of observed stream flow. We can take what the model is predicting at the outlet of those and compare it directly against what is observed to do the calibration effort. And as we're calibrating, there are a number of key metrics that we look at. Guiding all of this is the RAA guidance documents that require us to have hydrology predicted within plus or minus 15% of observed conditions. Now, this is on annual volume. That's what the RAA guidelines stipulate. Our modeling effort, we wanted to give ourselves a slightly higher standard where we look at the performance not only during the annual, but also during wet weather and dry weather, during storm flows and dry flows, and then the wet season and the dry season. So the p-bias is essentially it's a relative mean error with a negative sign on it, but essentially it's the percent error of the model versus observed is what we're looking at. We also look at a couple of other metrics, the Nash-Sutcliffe model efficiency metric, as well as R-squared of model versus observed. All this helps to build the evidence base that our model is representative of observed conditions. For phase one, we established parameters using smaller drainage areas that were fairly homogeneous. I mean, there's no place that's exactly homogeneous, but areas which are predominantly one land use type or another can help us to, when we go to them during parameter establishment, to make sure that we're setting parameters for those areas that are representative of the predominant land uses there. And then also, those areas did not have a lot of, or any of those hydro modifications that add that extra complexity to the system. So by doing that, we can set parameters, feel pretty confident that, in isolation of all those other movements, the hydrology is relatively representative of what's happening. Keep in mind, we also have the meteorological variability that's changing. So even though the HRUs may be parameterized the same way, we'll get a different response across our study area just because it's wetter in the foothills than near the coast, and so on. So that's all that texture is there as part of the model development system. And as we go from parameter establishment to the tuning, we zoom out a little bit more, we get into a little bit more of a mixed HRU environment. And you can see these highlighted gauges here represent the drainage areas to those phase 2 parameter tuning gauges. So all those were a number of additional locations where we looked at the model performance. Examples of ways that we look at model performance. Here are time series modeled versus observed. The observed data are plotted as the blue. The modeled data are plotted as orange. On the secondary axis, we have precipitation. In this case, we're looking at daily CFS in the stream, modeled versus observed over a 10-year period. And here we have the same information aggregated on a monthly basis. So it's another way of looking at the same data. It gives us a way of assessing the seasonality of the system. We can take all of that data and annualize it to look at what's happening across seasons, across all years. So this is aggregated across the entire 10-year period, all the Octobers, Novembers, Decembers, and so on, modeled versus observed. We can take that and plot it on a one-to-one, calculate some statistics that we can use to inform our decisions as to how we're going to change the parameters and so on. All that is part of the calibration process. During calibration, we do encounter, every once in a while, you'll see unrepresented storms. Here's a case where the rainfall record shows this really sizable storm, but the observed stream flow gauge didn't seem to wake up at all during that time when there was that significant rainfall event. Clearly, this rainfall event occurred and it was observed at more than one location. And so digging further, we can look at the observed data record and see that there are flags within that data record to show the quality of the gauge observations. It's not everything is always perfect. In addition, you can't, although we try to not blame the observed data, there are cases where re-examination shows that something was missed. Everything is subject to error. And so during the course of model calibration, we went through the effort of also looking at the quantity and quality of the observed, not only the meteorology, but also the stream flow and water quality data, so that when we compare our model to it, we have a point of reference to know how much weight to put on the over prediction or even the exact prediction of what was observed. Another key element of this process, base flow in this watershed is something very different than what you might find in other more natural watersheds. Most of the channels are concrete lined. Any flow that's happening during dry weather is probably not natural. It's coming from urban runoff, either associated with irrigation or maybe somebody empties their pool. Other sources that are anthropogenic that are contributing to this low flow that we're observing in the stream. And when we look at the model performance during low flow, we always have to remember that it is not a natural low flow situation. In this case, the bottom graph zooms in to the very lowest of the low flows. And you can see the model in the orange and the observed is not necessarily following as closely as the top graph, where you see that the model is able to capture the storms. In this case, if you calculate a % error on low flows, sometimes you were talking about like flows that are single-digit CFS values. If the observed data say the flow is 2 CFS and your model says it's 4 CFS, that's 100% error, right? So when you're interpreting the error statistics on low flows like this, you have to always remember that it is probably a situation such that it's, does that make it wrong if the error is at that level when we're talking about flows like this? And so part of the interpretation of the results just is always to remember what it is that we're shooting for. And our objective is to develop a representative model. A model can still be representative, even if it's not matching exactly 100% with those small flows. So finally, when we have calibrated established parameters at the small phase 1, calibrated and done some tuning at phase 2, the validation then is where everything comes together, and we have included the water reclamation plants, the spreading grounds, interbasin transfers, mixing and infiltration of water at these spreading grounds and debris basins, all of those incorporated in there. We look at what's happening as the water is routed to the most downstream elements of the system at these most downstream gauges. If our model is still able to tell us what is happening there within the range of criteria that were established for evaluating the model, then we can say that we have validated the hydrology across the system. So that's our goal here, is to look at the performance across small, medium, and large watersheds. So the p-bias, it shows very good. And so what you see on this graph, we see the phase 1 calibration sites, the phase 2 calibration sites, and then the validation sites grouped here on this graph. The green is red with this color gradient, where the darkest of the greens is the very good, meaning we were less than 5% of the observed. The satisfactory, the lightest green, means that we were meeting the 15% criteria on an annual basis, or the corresponding adjustments for the seasonal basis. So at the end of the day, we felt very confident that our model was, one, based on the RRA guidelines, we're meeting all of the satisfactory requirements for the RRA, and then two, zooming in to look at wet weather, dry weather conditions, the model was also performing in a quite robust way across all those conditions. So just to recap, all this, when we're interpreting results from this, the model was developed as a regional calibration. So we have the same set of HRU parameters across the board, regardless of where you are. The model is going to behave differently because we have high resolution meteorological data that changes. And so the same HRU in a wet portion of the watershed versus a dry portion is going to give us a different response, but it's still a consistently calibrated model in terms of the parameters that are driving the physical processes underneath it. As we go in to look at RAAs, and we'll get into some examples later on in the presentation, there may need to be some fine-tuning in certain areas. You know, if our low flows in a particular area were a little bit higher in terms of the air, there might need to be some fine-tuning of the calibration. There might need to be some investigation of some of the gauge data a little bit more closely. Also, special considerations for dry weather flows, other impoundments, and water movements. Not all of them were represented in their entirety. We did our best to capture the best available based on the information that we had. But if you're doing an RA in a very specific stream and you check the model results in that specific area, there may need to be some fine-tuning. But overall, this is an amazing starting point for all the RAAs. And that was the goal of this effort, is to provide a really solid starting point that meets the RAA guidelines at the key gauges that were selected for calibration and can serve the region well and provide a consistent basis for RAAs going forward. Water quality, similar to hydrology, followed a phased approach as well. The phase 1 was to establish some initial parameters that were based on the best available information and the efforts and the lessons learned through some of the EWIMP processes and so on. Phase 2 was to look at land use-based parameters and fine-tune it a little bit closer to represent different HRUs. Phase 3, watershed scale calibration, similar to the way we described hydrology, and then ultimately a larger regional validation. We'll go through some of these and we'll explain what was entailed in each of these steps. For phase 1, the initial parameterization, we started with what was parameterized in the original WMMS. Now remember, we had 20 HRUs in the original WMMS, 96 in this one. So mapping those 20 to the 96 is pretty coarse, but we can go in there and then have rules that are based on soils, slope, or high recharge to refine the initial parameterization across our 96 HRUs. The other thing was to look at some of the experiences that were documented in the RAAs. We had the privilege of working on many of these RAAs in the region. And so it was nice to be able to memorialize some of the efforts that we had done and the lessons that we had learned from those efforts into the WMMS 2 modeling environment. And there are many examples, not only in the LSPC side, but also from the sustain side of some of the improvements and refinements that were done to not only the calibration, but the modeling system itself. We got to incorporate all those into the hydrology and into the water quality calibration effort. Now, in phase one, let's just talk a little bit about the key processes that were involved. And we've done this by looking at the constituents. Ultimately, at the end of the day, we're going to use this model to inform the RA process, which is going to be for managing stormwater for metals, and nutrients, and other constituents. One of the things that we take away from this is the metals and phosphorus. These are going to be delivered with sediment. And so sediment was modeled as part of this effort. We did a very process-based sediment, but the purpose of that was to be able to make sure that the sediment-associated constituents were representative, and the timing and delivery of the load pulses followed the delivery of sediment. It's very important in the sustain side, because ultimately when you're talking about managing the stormwater runoff, being able to capture nuances like first flush loading pulses can have a strong impact on how you choose to manage that stormwater. And so making sure that in our watershed model, at the most upstream point, we're making sure that the processes for modeling these are representative. This was key. Another thing that you'll see in here is the dry weather flows. Now, the dry weather flows, as we mentioned, are not natural base flow. It's mostly urban runoff. And so during irrigation, there isn't any sort of force that's causing the mobilization of the pollutants. And so for the dry weather flows, we used an EMC. And so that was just a straight concentration associated with the dry weather runoff from the irrigation overspray HRUs within each of these subwatersheds. So that's what gives us our dry weather response. When we go in stream, we have settling and resuspension of sediment and associated pollutants, or first order decay of some of these other constituents as well. But the key is being able to represent edge of field, edge of stream pollutant loadings, which are going to be the boundary condition for sustain for stormwater modeling. That's one of the key objectives. And then making sure that when we compare our model versus observed in stream, we're also representative of the spatial variability, the HRU distribution, and the types of activities that are happening in various portions of the watershed. Phase one, initial parameterization. Here's a schematic that shows the physical processes that are represented with sediment. We model the generation and transport of sediment from the land surface as well as in the stream. For water quality, the pollutants that are sediment associated, we have a sediment concentration, these potency factors. So it's pounds of zinc per ton of sediment, for example. And that can vary by HRU. So certain HRUs where you're going to have either road traffic or parked cars, you would expect would have a higher potency factor for some of these metals than other pervious HRUs, and so on. So that's the nature of the texture. SOQC, that's the concentration associated with the dry weather runoff. That was set for the irrigation overspray HRU. 1 out of the 96 HRUs was irrigation overspray, impervious areas which receive some of that irrigation overspray and has a concentration when it's reaching the streams. And we'll show what the effect of that was ultimately in the model. Buildup and wash off is used for sediment on impervious surfaces, and then also for constituents like nutrients, which have a slightly different behavior than the straight sediment associated metals and phosphorus. So here's a view of the dry weather runoff concentration. This was kind of a neat element for us, you know, as we were modeling this, we looked at the observed data. And so what you see in the bottom graph there, the orange lines represent the modeled concentrations of total copper, and the blue diamonds, those are the observed data. You'll see that some of those blue diamonds have red circles around them. The red circles represent samples that were taken during the highest 10% of stream flows. So those are wet weather samples. So any blue dot that does not have a red circle around it, that is a dry weather sample. And when we looked at the dry weather flows, we were seeing some elevated, slight elevation of those flows. And the only way that you can get that is to have some kind of copper coming during the dry weather. So we go back to hydrology and we look and we see there's a small urban stream flow signature caused by runoff from during dry weather flows. These concentrations that are shown in this table come from literature and other sources that can help us to inform what we might expect in terms of dry weather runoff concentrations. When we put in these values and ran our calibrated model for hydrology, we saw that the model was waking up to those slight bumps, as you see by the circled yellow signatures. Really exciting for us, you know, geeking out on this on the modeling side. It's like, yeah, we nailed it. We know we have some idea of what might be causing those dry weather elevations. It made sense. It was seemed defensible, and we know that this is an activity in the watershed. At the same time, it doesn't represent a whole lot of load, but it is some feature of the watershed, and it was just neat to be able to check the box and say that, yeah, at least that piece of the model is also represented. So for phase 2, we did parameter tuning at land use specific areas. I'll let Steve comment on this portion.
Yeah, so John talked about, you know, we have 96 HRUs. We have an initial parameterization based upon all the good work that's been done in the LA region over the last decade. But when you're trying to match monitoring results at the bottom of the watershed, how do you know which knob to turn or which HRU that you're going to vary? That's always been a challenge. One of the components of the HRUs is land use, and it's generally understood that pollutant loading is different for different land uses given the types of practices that occur there. We're fortunate in the LA region that back in the mid-2000s, Squirt provided a pretty robust study where they had these small homogeneous land use sites up in the watershed, and they collected multiple samples throughout the storm duration for multiple storms at these sites. And back in the mid-2000s, us modelers utilized that data to calibrate some land use specific parameters that went into models that were used for TMDLs. They went into the original version of WMMS. We further tested those parameters, and now that we have the reconfigured model of WMMS 2.0, it's important for us to return back to that original land use data sets to see how we do. And then in that way, we are able to establish some ranges of parameters associated with those land uses that we know we can turn those knobs within those ranges during the calibration process to do some fine tuning. And so what you're seeing here are different types of land use sites. If you look on the x-axis, there's 3 different high density residential sites, and there's 2 different low density residential sites. You see the ranges of the observed data and the number of samples. So in the first column, there were 30 samples. That's land use 01, which was a high density residential site. And you also see the modeled hourly predicted concentrations throughout the durations of those storms. So they're all, you know, they correspond to those periods that the storms were collected. So that you can see there's 293 hours for the number of storms that were collected at that land use site. And so you can see that our ranges of the observed and the ranges of the modeled compare fairly well. So we have an understanding of the variability that we can expect for the modeling parameters for each of those land use sites. So these are residential sites. You get the next slide. There's some commercial sites, industrial sites, transportation. So this becomes our starting point to then hand over to John when he gets into the next phase to then know which knobs to turn during the watershed calibration process. John?
Awesome. So I start off with some initial parameters for my 96 HRUs. And now I can go in and select and look at how the model is responding when we mix these together at 3 of these key calibration sites. Now we picked Ballona Creek, Dominguez, and Malibu for various reasons. Ballona Creek, one, because it's fairly typical of the landscape that you see in most of the region. It's representative of the urban, residential, commercial mixes. We also have a situation in Ballona Creek where there aren't any point sources. And so it makes it kind of an isolated case where we can just look at it in terms of its ability to show us the story of what's happening from runoff water quality in isolation of other types of activity. Dominguez Channel gives us similar situation, a slightly different mix of HRUs, because now we're looking at a little bit more of the industrial, signature in terms of the types of activity happening there. And Malibu Creek is a relatively natural of the urban watersheds. It's more natural than the others. We also have a point source in Malibu Creek, the Tapia Water Reclamation Plant, which does an excellent job of managing the discharge during wet weather and then not discharging during the dry weather periods of time. So it was really neat to have these 3 sort of samples to look at and tune the model. And so we calibrated and validated the response at those sites. And then we calibrated at those 3 sites, and then we validated at these 3 additional sites, the Coyote Creek, Los Angeles River, and San Gabriel River. Now, these validation stations are just about as big as you can get. It's most of the study area represented here. You have a mix of HRUs. You've got hydro modifications. You've got Whittier Narrows Dam. You've got interbasin transfers. And so when you start to put all this together and really test the model in terms of, can it predict what's happening at the bottom of LA River? It was really encouraging from our point of view to see the model after doing the fine tuning at the land use level, calibrating at the small watershed level, and then ultimately validating at the large scale. To see all these come into line, it gave us a lot of confidence that the way that we had parameterized and configured the model provided and produced a robust representation of the system for further use in RAAs. So here's an example of the model versus observed calibration in Ballona Creek. And you can see that the model does fairly well. This is a view of sediment. The criteria that we used, similar to how we have regional board guidelines for the RAAs for hydrology, the 15%, we have pollutant-specific criteria in the RAA guidelines. Sediment was 20, 15 for nutrients being very good, and then heavy metals 20. Satisfactory was the lowest bar that we needed to meet in order to classify as meeting the RAA guidelines. So we looked at all these and we said, you know what, we are going to look at nutrients, which is the most stringent of these, and adopt that as our high end for very good. And then at the very low end, we're gonna bump it up even a little bit more. So instead of 35% being satisfactory, we said we'll say 30% be satisfactory. So at the end of the day, this first row, all conditions, that's what we have to meet for all the pollutants, regardless of what it is, nutrients, metals. That's what we adopted as our criteria for evaluating model performance. Now, when we look at wet and dry seasons, we mentioned how we also want to look at that because we want to see that our model is representative and reflective of storm versus dry, wet versus dry conditions. And so we also have criteria that we adopted for those. As you can see, it's very similar to what the RAA guidelines were for metals. This is for the finer resolution temporal evaluation of the model performance. So sediment is our view of things. We see a lot of green in here. We modeled sediment, as we mentioned earlier on, because a lot of the pollutants are sediment associated. So if we go to the metals then that are associated with sediment, we see copper, lead, zinc, cadmium. It was green across the board, across our calibration and validation stations, meaning that the darkest green meant that it was meeting the highest criteria. The lightest green meant that it was meeting the satisfactory criteria. This was really encouraging that for a regional model where we have the same parameters for all the HRUs, regardless of where it is, and we have the variability of the rainfall as we represented, and we have the hydro modifications and the movements of the water. After we put all that together and we mix it all together, the model is showing that it's a robust predictor of the existing conditions. And so as a great starting point for RAAs, we felt very confident that what we were providing for LA County was something that would be of use to them and also other stakeholders in the region as we plan stormwater management going forward. Similarly, for nutrients, we see nitrogen and phosphorus, also lots of green across the board. Water quality validation. I'll let Steve also comment on this element of the effort.
Thanks, John. So as John mentioned, this was a regional calibration that was performed to do the best that we could at a regional level, understanding that this was going to be the starting point for future watershed-specific calibrations. For instance, when the reasonable assurance analyses are updated in the future for each watershed management program, there's further calibrations that would be performed for that watershed to meet the RAA guidance, and there's a demonstration that's required as part of that RAA. However, the data sets that would be used for those additional calibrations are available now. The coordinated and integrated monitoring programs, the CIMPs, that all the watershed management groups have been investing in. They're still in their infancy, they're 3 years in or so. But I just want to commend folks on that effort. As modelers, we've never seen a data set that robust before. It's at a regional, for regional calibration, it presented some challenges in terms of organizing that data in a meaningful way, but it provided us an opportunity to do a snapshot comparison to that data, provide some early indication of where some improvements can be made for the next phases of watershed-specific calibrations that would be performed as part of those RAAs. But it gave us a starting point. So here's just a summary of some of the data that was collected. The list goes on, so we just made this table look like it goes off the page, but it's quite a long table. We organized different gauges by watershed management group, and you can see not all constituents are sampled at each individual station, but we still wanted to provide a meaningful way to consistently compare all the data from all the stations from all the constituents. And so what we did was we grouped the data by the different watershed management groups, and if there was only a couple of stations, we might group those with another watershed management group. I talk about this because I'm gonna, in the next slide, John, you can go ahead and transition. We show some of those groupings. So this is an example of the Bionda Creek watershed management group had a number of stations. And there was one station in Santa Monica Bay, J2, J3, that was, didn't want to leave it by itself as we were showing the model results. We grouped it with the Bionda Creek. You go to the next slide and you'll see a plot similar to what I showed you for the squirt stations. Each one of these are now SIMP stations. The first 3 stations that you see on the x-axis, again, what we're showing here is the observed data and the number of samples, and then the modeled concentrations at those corresponding locations. The first 3 stations that you see there are moving from upstream at BC01 NAT, which is national, and moving downstream to BC02 ING, Ingram. And you can see that we hit the top 2 results. The model results match the observed data pretty well. You get to the most downstream station at BC02 ING, and the observed data has a higher concentration. So for some reason, we weren't matching that. There's actually tributaries to Sepulveda Channel, which is the next station shown there, SCCUL. However, we matched that concentration observed there pretty well for copper. And so there must be something else that's contributing, another source, another reason why the observed concentrations are a bit higher and that we're not able to match in the model, which just points to further investigation that can likely be performed, or maybe even just using the model to tease out some further nuances that are specific to that watershed, but aren't necessarily meaningful for regional calibration. So this just gives one example of some insights, and we talk about this in the modeling report, that might want to be considered as further calibrations are performed for specific watersheds. Next slide, John. Similarly, here's a summary of the gauges that are located in the Malibu Creek watershed. You go to the next slide. Again, you're seeing here the comparisons within the Malibu Creek watershed gauges. The trends, the model matches the observed ranges pretty well. One thing I did want to point out is the number of samples. So the number of samples vary for each station. Again, the SIMPs are just beginning. We expect more data to be collected over time, and that would enable more robust statistical analyses to be performed both on the monitoring data and through comparison with the model results. But just as an example, the second to the last gauge on the right, you can see that one station had only one sample, which creates some challenges when you're trying to compare to model results. It's not necessarily representative of statistical range, but it's important to consider those number of samples when you look at those ranges here. And so, you know, some of the stations had 7 samples, some had a little bit more. And this trend continues as you look at the scent data for all the other watershed management groups. So there's quite a few of these plots. Again, it's just meant to provide a snapshot validation and help begin the process for further calibrations that would perform for the REAs. All right, John.
All right. Excellent. So now we're going to do a demonstration of LSPC. So we'll start off with the LSPC map user interface. This is what I mentioned is the web-based interface that is showing the model. So we're going to switch over to that application. And this is an experience that we've provided to help the user to interact with the model. And so what you see on here is the study area. The entire model study area is shown here on top of a satellite image. The model also allows you to toggle over to open street maps, where you can see relatively where the watershed is relative to other landmarks. So this is pretty helpful when you're modeling an area to have that point of reference. So this is what the interface looks like. Now, some of the core functions that are available, we are allowed to interact with this shapefile. Let's say I wanted to model Los Angeles River and all of the watersheds that are hydrologically connected to Los Angeles River. From here, I can come into my selection window, and when I click on this toggle switch, I can either select a single sub-watershed to model, or if I toggle into the upstream and I zoom into the most downstream outlet, the model actually allows me to select the most downstream outlet. This is the outfall at the bottom of LAR. And if I zoom up, behind the scenes, it has selected all of the sub-watersheds that are hydrologically connected to that point in the network. And then I can proceed from here to go and run that model if I so choose. We'd be probably waiting here for about an hour for that to run, so I'm not going to do that. But for just sake of demonstration, I'll also show you another feature. Let's say you select your favorite sub-watershed and you want to kind of memorialize that within your interface so you can go back to that at another point. The tool allows you to save those here as plans. So in this case, Los Angeles River is a plan. There's also a Malibu plan that has all been created here previously. And if I click on that, you can see it's highlighted the watersheds that are associated with the Malibu Creek watershed. Now at this point, I can press run and it will launch the LSPC interface and allow me to interact with the model. Just for the sake of expediency, I'm going to go ahead and pick a really small watershed. First, let me clear my selection window and then select one small watershed here. So this is all the watersheds that are hydrologically connected to that. When I press the run window, LSPC is going to bring up this first dialog screen, which allows me to tell the model which parameters I would like to see run. And the reason why this pops up is because I have this advanced toggle on. So this is what we would use because this allows us to change things and view the parameters and so on. In the case where you don't want to do that, you can also turn off that toggle altogether. And what will happen is LSPC will just open, query that subset, run the model for you, and then you'll have the results in the output folder. So in this case, the model is getting the results. It's querying the database and grabbing for us the instance of that subwatershed. It's querying the database for all the HRUs that are upstream within that drainage area, as well as all the weather stations. It's probably just one associated with this subwatershed is going to be assigned, and it's going to generate for us an input file of just that one subwatershed. Now, this is one of the key advantages here. There are 2,655 subwatersheds, and it's not every time that you want to run all of those. If you have a specific interest in a sub portion of the area, you can just run that one subwatershed that we have selected. In this case, that's what we've shown here. So here it allows you to go in, you can look at your stream network. There's just one subwatershed that we picked, which was 6972, whichever one that was there. It has within this area my HRU distribution. So this has the different types of HRUs. There's a specific index for them and a description about those HRUs. The HRU attribute table, it has all the slots for all the possible 96 HRUs are available for each subwatershed. This is just one subwatershed, so it's nice. We have 96 records in this table. The area of each of the HRUs is shown here. I can go in here and I can say, let's run a 10-year simulation. Let's run a 20-year. I can change the period of record that I want to run in here. There's a model simulation period and an output simulation period. The convenience of this is it allows you to have a spin-up period that you don't include in your roll-ups. That becomes important because at the end, when you're looking at model outputs, there are not only you have the time series outputs, but the model also provides this really handy summaries of all the land uses, the stream information, if they're point sources. It can summarize that on an average annual basis. These are really convenient tables for use in generating heat maps. So you can calculate edge of field loading by subwatershed and make a heat map of that. And you can query that by HRU. And you can do subsets. You can, the box plots that Steve was showing, you can query the model and generate box plots of those results by HRU as well. So really handy summaries. And all this is going to be based on the output simulation. So it's thrown out the spin-up period. So just to show you some of the features of the model here. The custom output, you can pick the standard output. The custom output exposes all the different elements of the model that you can output. In this case, we've chosen precipitation. We've also chosen to show RO, which is the reach outflow, sediment concentration, and then conc out, which is the flow weighted average concentration out of each reach segment. In this case, it's just the one. And all this is here. When I'm ready to run, I can click my run button and the model is going to start executing. It's going to run this sub watershed. Of course, I picked 10 years. This is just one sub watershed for 10 years. It shows you it takes about a minute for that to run. And so as you expand your watershed and the number of sub watersheds in your areas, it'll scale accordingly. Of course, in the background, it's running all the unique HRUs. So there are some efficiencies gained even as you get larger because it's not going to run every single one. It runs the unique HRUs and then extrapolates that. So there is some efficiency gain there. Well, while that's running, I'm going to show another output file from Ballona Creek. This is from Malibu Creek pardon me. So this is one of the outputs that we had run just previously here. The outputs that I chose to show were precip, as we saw, RO, which is the stream flow at the outlet of the subwatershed. I also have my sediment concentrations. 1, 2, 3 represents sand, silt, clay. Set out is the total suspended solids concentration. And then the concentrations of each of my water quality constituents are shown. The format of this output file is fairly simple and straightforward. It gives you the opportunity to see that the order in which the constituents, the outputs are listed here, corresponds to the order of the columns in each of these files. So we have our subwatershed outlet that we're simulating, as well as the year, month, day, hour, and minute, followed by each of the constituents. Precip in the first column, reach outflow in the second column, sediment in the next 4, and the water quality constituents, and so on. So this is LSPC map. This is just the interface that we provide for interacting with the model. It's a fairly convenient interaction with the model. We also do have the map interface that is through the WMMS website. So we'll toggle over that right here. All right, so I'll switch over to this view. Here we have the landing page for the WMMS web-based interface. So here it allows us to look at some of the key components of the model. Here it describes the system. From this page, and we'll go over this in the rest of the memo, there are other utilities and other documentation that we can go into. But right now, what I want to highlight is this is the landing page. From here, if you don't necessarily want to go and run the model, there are some of the outputs that have been run and pre-configured for viewing here. So let's say I want to look at Arroyo Seco. I go to one of these assessment points that's listed here, and I can click on that. And when I do, it gives me a view of the time series for Arroyo Seco at this outlet. This is pre-run at this point, and it gives me some summary statistics of the flow. I can toggle over and look at sediment. I can look at some of the other metals, concentrations, lead, and so on. All these constituents are available for me to interact with here. And if I'd like to look at the time series or do some other analysis with it, I can click this button here to download the time series. And it downloads for me and opens up in my viewer after downloading this file. And this is the same file that we saw before, except this is for Arroyo Seco outlet 6402, right from the web viewer. So this is a nice, convenient element there that is available for the users as well. You know, and if you want to go back to this page, there are other things that you can look at and interact with in this interface.
So just to pick up, John, so this is a user-friendly tool that we made available for mostly non-modelers. There's select locations or assessment points that we made available. So this isn't providing output for all the individual subwatersheds in the model, but it's some convenient locations that would be of interest to many folks who want to pick some pre-run results and download them, as John just showed. And as John mentioned, this is the landing page for the WMMS framework. We're going to go through a number of these other utilities in the optimization viewer and some of the tabs you see at the top. But John, if you can click on the documents, data, and downloads for 1 second. And then go ahead and scroll down, accept. So this is where the documentation, so you can see there's there's the LSPC model, we talked about that. The sustain model, we're going to get into that in the second phase of the training session. But if you scroll down, John, you can see that there's a phase 1 and a phase 2 report. So much of what we would discuss provided a summary of the phase 1 baseline model. That full documentation you can download from the website here. The next phase of the training session, we'll get into the sustain and the optimization framework. There's a number of utilities here. Dustin's going to give a full tour of the system. I just wanted to point out that this phase 1 report is a pretty dense document, provides all the details of everything we just discussed about the LSPC model development, calibration, and validation. So we're going to pause here. And if those who want to continue with the training session associated with sustain and the optimization framework, that will be continued in the phase 2 of the training course. So thank you for attending, and look forward to seeing you in the next training session.
Yes, thank you.